Hi, welcome to the lecture on section 4.1. So this lecture, we're going to go back to 4.1 because we started with 4.2 where we saw how to use Laplace transforms to solve differential equations. Now we're going to go back to what is the definition of the Laplace transform and where does this come from? So we'll start by looking at the definition and then we'll do a few examples where we practice how to use the definition to find the Laplace transform of a function. And yeah, so let's start there. So this is the Laplace transform of a function. And you notice, first of all, that it's an indefinite integral, well, anyway, it's an integral from 0 to infinity. And we are integrating the function f of t here, but we're multiplying that by this e to the minus st. And if s is positive, then this function will go to 0 quite rapidly. So as long as this function f is not growing too quickly, together this function will decrease quite rapidly, and we will get something reasonable by integrating from 0 to infinity. Okay, so let's give this a try. So we're going to use this definition to directly find the Laplace transform of f of t equals t. And we know from the table of Laplace transforms that the Laplace transform of this function is 1 over s squared. Okay, so we saw that last time. 1 over s squared, yeah. So that's what we're expecting to get when we apply this definition. So let's apply the definition. So the Laplace transform of f of t is this integral e to the minus st and then times f of t. So this is going to be, and let me just say this is f of s is equal to this. So times t dt. Okay, so how do we do this kind of integral? So this will be the limit as b goes to infinity of the integral from 0 to b, and then t e to the negative st dt. Okay, so in order to do this integral, I think what we need to do is integration by parts. So integration by parts will let us take the derivative of this t, and so we'll be able to have this t disappear. And then at the same time, we're going to integrate this, which is not going to be a problem. So what is the rule for integration by parts? So the way I remember this is, I know it comes from the product rule. So if we integrate both sides, then we get the integral of fg prime plus the integral of f prime g. And let's take this one to one side. So we'll have fg minus the integral of f prime g. Okay, so that's sort of what we're after. So there's our integration by parts. Okay, So I'm going to let this t be the f. And then this term here will be the g prime. So the first thing I need to do is I need to integrate this e to the negative st. So this is going to be t e, so integrating. So this will be, let me just make room for this. Okay, so this negative s e to the st, this is the integral of e to the negative st. Okay, so there's that, and that's going to be evaluated between 0 and b. And then we have minus the integral from 0 to b. And now we take the derivative of f, which is 1, and we have g, like that. Okay, so let's evaluate this first term here. So we have negative b over s, e to the negative b, oh sorry, not the s, e to the negative s b, and then minus negative 0. So if I plug 0 in, I'm just going to get 0. So there's a 0 there, so the whole thing becomes 0. So I'll just write minus 0. Okay, and now let's do this integral here. So it's minus the integral of this, so it's minus 1 over s e to the negative st from 0 to b. Okay. Okay, so minus, so when I plug 0 in here into this, when I put 0 here, then this is 1. So I get minus 1 over s, so it's plus 1 over s. Okay, let's see, make some more room here. So I just want to simplify this expression. Okay. All right, I'm just going to take a moment to make sure everything's okay. Yeah, that's what I thought. So I realized I did make a mistake. I was wondering why I wasn't getting 1 over s squared. So my mistake was back here. So this should have had a negative 1 over s in there. So it's not the original thing, but it's the integral of that. Okay, so what do I need to change here? So then this is going to be 1 over s squared. One over s squared minus 1 over s squared. Okay, there we go. All right, so now note that if s is a positive number, then when we take this limit, this is going to go to 0 because this is a negative number. So as b gets larger and larger, this will become very, very small, and it'll go to 0. And this will also go to 0 as well. So both of those go to 0. So we're left with 0 minus 0 plus 1 over s squared. And so we get 1 over s squared. Okay. All right, let's do the next one. Okay, so in this case, I guess, do we know what the Laplace transform would be from the table? So I guess I would write this as f of t is equal to e times e to the 3t. And so then the Laplace transform would be e times the Laplace transform of e to the 3t, which is 1 over s minus 3. So that's what we're expecting to get. So let me write it this way. So we expect to get e over s minus 3. That's the answer we expect. So let's apply the definition. I mean, I guess I don't really need to write this. So it's just, this is the definition. So it's e to the negative st times f of t, which is e to the 3t plus 1. So we have e to the 3 minus s t, and then times e. Oh, this is b. So this integral will be 1 over 3 minus s e to the 3 minus s t times e from 0 to b. So plug in b, and then minus, and that will be 1 times e. Okay. So now if this S3 minus S is negative, then this term here will go to 0. So we're thinking about 3 minus S is negative. So in other words, S is greater than 3. So usually there's some sort of an interval or a range for S to be valid here for these Laplace transforms. So if S is greater than 3, then that term will go to 0. So we'll get 0. And then here we'll get plus 1 over S minus 3 times E. And so we get E over S minus 3 as we expected. Okay. All right. Let me see. I can just delete this page. Okay, so one of the great things about Laplace transforms is that they are, we can use them on functions that are not continuous, that have some sort of a jump discontinuity like this. And this is especially important because there are certain applications where you want to solve a differential equation that involves a function with a jump discontinuity like this. And this is especially important in things like analyzing circuits, so electrical engineering, where you'll have like a switch, which is turning on and off at certain times. So Laplace transforms give us a perfect way to be able to deal with these. Oh, my dog is throwing up. 1 second. Okay, got that taken care of. So let's look at this. So we were talking about looking at the Laplace transform of a function that has a discontinuity like this. So what is the Laplace transform using the definition? So it's the integral from 0 to infinity of e to the minus st times the function. Now, this function has 2 pieces. So the first piece is from 0 to 1. And there the function is equal to 1. And then there's another piece from 1 to infinity. And there the function is equal to 0. So that second integral will be equal to 0. So it's just this first integral that we need to evaluate. This first integral is going to be negative 1 over s e to the negative st. And then we're evaluating it from 0 to 1. So we get negative 1 over s minus times e to the negative s times 1. And then minus 1 over s times 1. So the answer is 1 minus e to the negative s over s. Okay, so there's the answer. Now we'll learn later on how we can use the table of Laplace transforms in order to write down the Laplace transform for functions like this. So there is a term in this table of Laplace transforms. It's this function called the unit step function. And this function is equal to 0 if for t less than a, and it's equal to 1 for t greater than or equal to a. So you can use this unit step function in order to write the function f of t above, and then we know what the Laplace transform of this unit step function is. So we'll look at this. Actually, we're going to come back to this in this chapter here. But then we'll go into it in more detail in future sections of chapter 4. Okay. Yeah, so the Laplace transform of this function is e to the negative as over s. So that's what it is. So, and we see this popping up here. So there's the e to the negative s over s, and we actually have these two terms. So we have 1 over s, which is 1, and then we have minus e to the minus s over s. So that'll be a minus this unit step function. So in fact, we could do the following. One minus this unit step function. And if you check this way to write the function is the same as this definition up here. So when t is between 0 and 1, then this term here will be 0. So we'll just get 1. And when t is greater than or equal to 1, then this term will become 1. So you get 1 minus 1, which is 0. So you get exactly this from that. Okay. Anyway, I guess that's not part of the example. That's just some comments. Okay. So normally we don't use the definition of the Laplace transform to work with Laplace transforms because it can be rather tedious, and we have this really nice table of Laplace transforms. So let's go through a few examples where we use the table in order to compute these Laplace transforms. Okay, so here we have the Laplace transform of 1, which is 1 over s, and then the Laplace transform of hyperbolic cosine 5t is s over s squared minus 5 squared, so 25. Okay, and we can combine these together. So we can get s squared minus 25 plus s squared over s times s squared minus 25. So we get 2s squared minus 25 over, if you want to factor it out, I guess you could write it, but let's just keep it factored. Okay. So it's a lot easier to use the table to do this. That would have been quite tedious to do with the definition. Okay, so now this one is special. So we have cosine squared. And if you look in the table of Laplace transforms, there's actually no cosine squared. And there's no way to even really multiply things. There's no rule about multiplying two functions together and getting a Laplace transform. So what we need to do is rewrite this using a trig identity. Now the trig identity is going to be based on cosine squared. Now I did this another time and I didn't have a lot of luck with it, but let me try this again. So let's see. So this will be pi over 2, pi, 3 pi over 2, and 2 pi. Okay, so this is going to be 2 pi over here. Okay, and then I'll have 1. Oh, maybe I'll make it 1 and minus 1. Okay, so cosine goes like this. Okay, and now I want to do the same thing. I want to square it. Well, maybe I can do it on the same graph. Let me do it on the same graph, but with a different color. So I'm going to square these values. So minus 1 squared is going to be 1, and then that's like that. Okay. So what we get is a function that goes like this. So that's cosine squared. And in blue, we have just cosine. Okay, so what does that tell us about cosine squared? So cosine squared then is going to be it's basically like a cosine, except it's double the frequency. So it's going to be a cosine 2 theta, and it's been shifted up by 1. So we have 1 plus, so that would double the frequency and then it would shift it up. But then the amplitude is divided by 2. So we get 1 over 2 times this. So that's that's my guess, and I suppose I should look this up before I go any further. So I think this is like a double angle trig identity. Okay, yeah, I found it. So I found there's an identity here that says cosine 2 theta is equal to 2 times cosine squared theta minus 1. So if you rearrange the terms here, move this 1 over here, and then divide by 2, then you'll get precisely this formula. Okay, so let's use this formula here. So f of t is going to be 1/2 1 plus cosine 4t. So I think we should maybe, well, no, I guess it's fine. So the Laplace transform is, it's going to be 1/2 times the Laplace transform of the stuff on the inside. So the Laplace transform of 1 is 1 over s, and the Laplace transform of cosine 4t is s over s squared plus 16. So it's s squared plus 16 plus s squared over s times s squared plus 16. And so then we get s squared plus 8 over s times s squared plus 16. Okay, so that's just because the 1 over 2 cancels, so you get 2s squared. So, but then divide by 2, so it's just 1s squared. And 16 divided by 2 is 8. Okay. Okay, so I believe I have a note about this one. So this one actually is going to require a preliminary integration by parts in order to compute its Laplace transform. Now, there is a rule here that involves t times a function, and it gives us a rule for getting its Laplace transform. So I suppose if we were to use that, we have that the Laplace transform of t times f of t is equal to minus f prime of s. So in this case, it would be, let's see, so the derivative of the Laplace transform of cos 2s, so that's s over s squared plus 4. So that means that we'll get let's see. Is it low D high, high D low? Boy, I always forget this. Never been a big fan of the quotient rule. Okay, low D high minus high D low. Okay. So let's see, s squared, so it's going to be s squared minus 2s squared, but then minus okay. So that's what we expect the answer to be. But suppose that we didn't know about this rule here. So this is one of the rules in the table. So if we didn't know about this rule here, then what would we do? So they're suggesting that we do it by using a preliminary integration by parts first. 1 second. Okay. So let's see how this goes. So if we want to do the Laplace transform of that function, then it's the integral from 0 to infinity e to the minus st times the function t cosine 2t dt. Maybe I can leave the limit stuff off for now. So let's do integration by parts. So the integration by parts is to remove this t. So remember what the rule for integration by parts is again. It's fg prime fg minus f prime g. Okay. So if this is f, then we'll take the derivative of it here. Then we also, yeah, and that'll be fine. So that term is fine. But then there's this term here. We need to have f and then g. G is the integral of this cosine 2t times e to the negative st. So that could be a little bit tricky, but let's see what happens. So maybe we need to know what this g value is first before we proceed. Yeah, okay. So what is that? What is the integral of e to the negative st times cosine 2t? So I think to do this one, we also need to do an integration by parts as well. So I'm going to let, I want to take the derivative of this. So this will be my f, and this will be g. So the integral of that is sine 2t, and then 1/2. Oh wait, what am I thinking? Integral of e to the negative, yeah, this. And then f. And now I can take g and the derivative of cosine t. So that'll be that over 2 over -2. Okay, let's clean this up a bit. Okay, now we'll do another step of integration by parts. And again, we'll take the derivative of this, and we'll take the integral of that. Oh. Oh, whoops. This 2 is going in the numerator. So that should actually go here. Let's see, that should be plus. Oh no, that's fine. Okay. Integrate that, yes, okay. And sine Okay, let me do this stuff again. So the integral, that is -2 over s squared e to the negative st times, now the derivative of sine, which is cosine 2t times t, or times 2. So this will become a 4 here. Okay, what do we get? Okay, so now the idea is we have this guy here, and that is equal to this one. So I'm going to move this term to this side of the equation and then solve for that. So I'm going to get 1 minus 4 over s squared times the integral of e to the negative st cosine 2t dt is equal to this stuff. Okay, let me do this in a couple steps. So this will be s squared minus 4 over s squared. And then on the right, I'm going to factor out the e to the negative st. And then we have negative 1 over s cosine 2t plus 2 over s squared like that. Okay, and so therefore we get s squared over s squared minus 4 e to the negative st times negative 1 over s. Oh, yeah, I could simplify this. So I could factor out this 1 over s squared, and that'll cancel that. So I'll get 1 over s squared minus 4 e to the negative st times negative s cosine 2t plus 2 sine 2t. Okay, so there's that integral that we'll need. Okay. All right, so where were we? So we got that integral down. So now what we're really after is computing this integral. So first of all, we're gonna do an integration by parts here. So let's see. Okay, integration by parts. So I'm going to use, this will be the f. So I get t e to the negative, oh, and then the integral of this, and that's where we need this expression here. Okay. And then minus the integral from 0 to infinity of t prime, which is the derivative of t, which is 1, and then this stuff. Okay. All right, I think we're getting pretty close. Let's see. So the top thing, we're going to have the limit as b goes to infinity. So this will be b over s squared minus 4 e to the negative sb minus s cosine 2b plus 2 sine 2b and then minus plugging in 0. So that would just be 0 because we'll put a 0 in here. So we'll just get, so everything will become 0. Okay, so that'll just be minus 0. Okay, and then this bottom integral, let me see, I can factor this thing out. And then I have, oh, actually, maybe I'll do it in a different way. So I'll do plus s over s squared minus 4, integral from 0 to infinity, e to the negative st, cosine 2t. Okay, and then minus 1 over s squared minus 4 integral from 0 to infinity. Need more room. Maybe I'll put this 2 out here. Okay. So this thing here, this is the Laplace transform of cosine 2t, and we know what that is. And this is the Laplace transform of sine 2t, and we know what that is as well. Okay, now the question is, what's going on up here as b goes to infinity? Well, I think all of this stuff is going to go to 0. So this will go to 0 much faster than anything else. This is bounded between -1 and 1. Same with this. So this whole thing never gets really big. So that this will go to 0. And then, yeah, that thing will disappear as well. So this whole thing is going to go to 0. Okay, so that's what that limit does. So the limit will be 0, and then we'll have s over s squared minus 4 times the Laplace transform of cosine 2t, which is s over s squared plus 4. And then we have minus 2 over s squared minus 4 times the Laplace transform of sine 2t, which is 2 over s squared plus 4. So we get s squared minus 4 over, this will be s squared, well, let me just write it out. S squared minus 4 squared, oh no, s squared minus 4. Yeah, s squared plus 4. Okay, that is not the same answer that we wanted. So we actually wanted to get this. So I made a mistake. All right, I need to investigate. Okay, I think I found my mistake. This is supposed to be a minus because there's a minus, minus, minus. So that should be a minus there. That was my mistake. So that's a minus, which makes this a plus. And then this becomes plus, plus. I think that's it. I think that's it. Okay. So it's a plus, plus, plus. Yeah, same thing. Plus, plus, plus. Ah, okay. Now we've got it. Now we've got it. So this will actually be s squared plus 4 squared. And wait, is that what we wanted? Yeah, that is. So let me just check. Perfect. Okay, that's it. Whew, what a question. That was rough. Okay, so that required a lot of integration by parts, but that's the way we're able to do it. So that's what would happen if we didn't have this nice rule here. So this rule lets us do this Laplace transform in a much easier way. And without that, we have to do this a lot of integration by parts in order to get the same answer. Okay. All right. So let me move this stuff up. Okay, now we're going to look at going the other direction. We'll look at finding the inverse Laplace transform. So on the table, let's see, where is this s to the fourth? Let's see. Okay, so there's a rule on the table that says, and I don't know if it's in this. They refer to this smaller table in the section 4.1. Yeah, it's the same. It's the same rule. So it says that the Laplace transform of t to the n is n factorial over s to the n plus 1. So that's what we have here in this case, but here we have n would be equal to 3, right? So n plus 1 is 4. So what would the Laplace transform of t cubed be? It would be 6. So 3 factorial is 6 over s to the fourth. But we have 3 over s to the fourth. So what would the inverse Laplace transform be of 3 over s to the fourth? It would be 1 over 2 times the inverse. Let me just put a box around this. Six s to the fourth. Okay, right. So 1/2 times 6 is 3. So and then the inverse Laplace transform of 6 over s to the fourth is t cubed. So we would end up getting 1/2 t cubed. All right, let me just rearrange this a little bit. Okay, 1 second. Okay. So there's that one. Okay, what about this one? So in the table, we have that the Laplace transform of e to the at is 1 over s minus a. So in this case, that means that with a equals 4, we would have the inverse Laplace transform of 1 over s minus 4 is e to the 4t. Okay, but we have this 3 in front there. So what does that mean? So we want to do the inverse Laplace transform of 3 over s minus 4. So we factor out the 3. And we get 3e to the 4t. Okay. All right, so this one is a little bit more involved. We have the Laplace transform. Well, maybe I'll write down as the inverse Laplace transform. So the inverse Laplace transform of s over s squared plus k squared is cosine kt, and the inverse Laplace transform of k over s squared plus k squared is sine kt. Okay, so that's what we'll use. So we want to do the inverse Laplace transform of 5 minus 3s over s squared plus 9. Maybe I'll drop this Laplace transform stuff first, because I don't want to keep writing that. So I'll split this up. I guess this 5, I'll move to the front. But then I know I want a 3 up here, so I'll divide by 3 here. And then here I have minus 3 times s over s squared plus 9. So now I know that the f of t, which is the inverse Laplace transform of f of s, is 5/3 sine 3t minus 3 cosine 3t. Okay. Okay. All right, so as I mentioned before, we're going to talk about this unit step function. So the unit step function is defined as follows. It's going to be 0 for negative t, and it'll be 1 for non-negative t. So it's this graph. So it's 0, and then when it reaches the value, when t is 0, it jumps up to 1, and then it's 1 forever. So that's the graph of this unit step function. Now, if we want to have this discontinuity happen in a different place, then we just subtract a, and that will shift this function over to the right by a. So now this discontinuity is happening at a instead. Okay, so we already saw what the, from the table, the inverse Laplace or the Laplace transform of this is going to be e to the negative as over s. So that's what the answer is. So let's see if we can get that by the definition. So the definition is going to be integral from 0 to infinity e to the negative st times f of t. And we know that it is 0 for t less than a, and it's 1 for t greater or equal to a. So this will become the integral from 0 to a e to the negative st times 0. So that'll just become 0. And then plus integral from a to infinity e to the negative st times 1. So the first integral is just 0, and the second integral is going to be, the antiderivative will be negative 1 over s e to the negative st, and then a to b. Okay, so for s positive, then this first term is going to go to 0 as b goes to infinity. So s positive, we get that this first limit is 0, and then we're just left with the second thing, which is e to the negative as over s. And so we get e to the negative as over s, which should match what we have up here. Yeah, okay. Okay, so we'll get more practice with this unit step function in a future section. But just know that it makes dealing with discontinuities quite easy. It's just a matter of figuring out how to write your function that has some discontinuities using this unit step function. Okay, so there's some material from section 4.2 that I skipped over when going over section 4.2 last time. So let's talk about it now. It has to do with the Laplace transform of an integral. So if you are integrating a function in the time domain, this actually corresponds to taking the Laplace transform of this function and then dividing by s. So as I mentioned before, differentiating in the time domain corresponds to multiplying by s in the Laplace domain, and integrating in the time domain corresponds to dividing by s in the Laplace domain. So this is a really easy thing to remember, using that idea of multiplication by s is differentiation and division by s is integration. Okay, so that means that if we want to do the inverse Laplace transform of some f of s that has a divided by s in it, then we just do the inverse Laplace transform of the f of s, and then we integrate it. So let's do a couple of examples like this. I think there's 2 examples. Yeah, just 2 examples. Okay. So what is the inverse Laplace transform of 1 over s minus 3? This is e to the 3t. So what does that tell us here? So based on that rule up there, if we want to do the inverse Laplace transform of this, we would integrate from 0 to t, and then we just integrate this guy here. Oh, tau. So you have to put a tau in here as the variable that we're integrating over. So this will be 1 over 3 e to the 3 tau evaluated from 0 to t. And so we'll get 1/3 e to the 3t minus 1/3 e to the 0. So that's 1. So there's our Laplace. There's the function corresponding to this guy here. And of course, we know that we could actually do the same thing using partial fractions. So we could have split this up into an a over s plus b over s minus 3. And that would have been another way to get this answer as well. So we would have found that a and b, a was minus 1 over 3 and b was 1 over 3. And then we would have gotten this. So you can use partial fractions to do this as well. But you can also use this rule about what is the transform of an integral. Okay, one more question here. So again, we can use partial fractions here, but let's try to do this with this, this rule. So what this is telling us is that we're dividing by s twice, so we'll have to integrate twice. So let's first write down what the inverse Laplace transform of 1 over s squared plus 1 is, and this will be sine t. Okay, so first of all, we're going to integrate from 0 to t. Okay, let me write this here. Okay, so it's 1 minus cosine t. Okay, let me write it that way. 1 minus cosine t. Okay, so now if we want to get this one, so s squared, we will integrate that function from 0 to t, 1 minus cosine tau d tau. So integrate that. And then plug in 0 and you get, you would get 0. So that's it. So that's the answer there. So t minus sine t. Yeah, and just to check, if I take the Laplace transform of that, I would get 1 over s squared minus 1 over s squared plus 1. And so that would give me s squared plus 1 minus 1 over s squared. Wait a second. What did I do wrong? One second. Okay, I'm being silly here. So it's not minus 1, it's minus s squared. Okay, right. Okay, so it checks out. Okay, so that's just a check, just checking. Okay, so yeah, so that's it. So that's how we can use this this rule on a couple of examples to see how that's used. But later on, we'll definitely be doing like partial fractions. So we can do either of these two questions using partial fractions instead. But I don't know, maybe this is easier to do than partial fractions. Okay, so I'll stop there and thank you for watching.